Cinque. Last lesson we looked at groupings of materials. We looked at metals and non-metals and all that stuff that was pretty much revision of chemistry. You needed to find some examples and definitions as well. So hopefully you finished that. If you haven't finished that, you should have finished that for homework. We're now going to look at properties of materials. This is really important stuff. When you discuss a property of an engineering material, you want to make sure you use the right terminology, and you want to make sure that you use it for the right material. So this is going to be a lesson that if you spend a little bit of time on, is definitely worth the effort. And properties of materials is the title that you're going to put in your notes. Of materials. And I've got some little acronyms that I use to try and remember this information, because it's really important that we try and find a way of putting all this into our brain boxes. So the first one I use is me, Mac, Pet. So this acronym I use here is the idea of me, Mac, Pet. And I write that box down, and that's how I remember some of the properties of materials. Okay, so this will all make sense in a moment, hopefully. So me, with a small e, is mechanical properties. And that is one of the ones that we really need to understand for engineering, how things behave mechanically, okay, when we're using the material. So mechanical properties. Then we've got magnetic, which we discuss later in the course. But we know what magnetism is. So some metals are magnetic, which means they're attracted by a magnetic field, and others are not. But later on we find out a lot more about magnetism, because magnetism, there's a lot more to magnetism than meets the eye and what you commonly think of magnetism. We've got paramagnetic, diamagnetic, there's lots of things that we need to learn. And then we've got chemical properties. And then for this one here, physical. And electrical properties. And finally, thermal properties. So lots of properties to remember, but if you remember me, Mac, Pet, okay? Me, Mac, Pet. If you remember that, you'll remember all your properties, okay? So, like I said, mechanical is the main one, and I'm going to show an acronym to remember that one. But, magnetic, is it magnetic or not magnetic? Ferrous, non-ferrous. Chemical properties, is it an acid? Is it a base? All those sorts of properties that you have for chemical. Physical, things like the density of the material is one thing that comes to mind. How much weight for a given amount of volume. Electrical, is it a conductor or is it an insulator? Can be very important depending on what use you want to put the material to. Like if you want to use it for an insulator, it needs to be an insulator. If you want it to conduct electricity because you want it to carry a current, it needs to be a conductor. And then thermal, okay? Does it conduct heat? Well, like a lot of metals do. A lot of metals conduct electricity. Most metals, I think all metals, conduct electricity and heat quite well. So, whereas other materials might be insulators, not only electrically, but also thermally insulating, so they don't transfer heat. And that, if you want a heat shield on a spacecraft for re-entry, things like that. So we've now got an acronym for remembering our properties of materials. So last lesson we did groupings, now we're doing properties, okay? And then for our mechanical, because I said that's a really important one, out of mechanical, there's a whole lot of properties in the mechanical section where we really need to know the terminology. And I use an acronym which is SHE's PMDFN with a small t. Now you might say, how am I ever going to remember that? And the way I remember that is I say, and I'm going to write it up here, she's the Prime Minister, defend large F, defend the Northern Territory. So she's the Prime Minister, defend the Northern Territory. And I write it that way, and that way I start to remember the words that we're dealing with. She's the Prime Minister, defend the Northern Territory. So what does that all mean? SHEPMDFNT, notch toughness. So each one of these letters represents a particular mechanical characteristic. Okay, and we're going to write down each of these characteristics. First one we should know, strength. Ability of material to withstand a load, okay? Ability to withstand a load varies according to the type of load, e.g. tensile, compressive, shear, torsional, etc. So all of those words, some of those words you probably don't know. But for instance, if you've got concrete and it's not reinforced, or stone in compression, if you make a post out of stone and you put pressure on it, it's very strong. But if you make a lintel out of it, a beam, and you try and support it at either end, in tension, if you were to apply a load between the two supports, it's quite weak. It'll crack and it'll break. So that's why we're saying strength is dependent on the type of load. So stone in compression is strong, in tension is weak. Okay, so torsional is twisting force. Some materials might withstand that really well, others may not. We've also got shear, which means we're pushing and pulling in different directions across the material. All these different things which we will study later on in the course. Main thing to know is that it's the ability to withstand a load, okay, and that load types, or the way a load is applied to a material, can vary. And we'll find out all about that and the wonders of that later on in the course. So that's strength. Then we've got hardness for the H. So that's strength. Then we've got hardness. And that's our ability to withstand abrasion, say scratching. And we quite often measure that on the Mohs scale, which is 1 to 10. And talc is at the bottom of that scale, it's really soft. And we go right through to 10, which is a diamond. And that's your hardness. So quite often something can be hard. It doesn't necessarily mean it's strong, because quite often as hardness goes up, brittleness increases, so the material will fail. So that's your hardness. Then we've got elasticity. And that's the ability to return to previous dimensions under load. So we apply a load and then we take the load away, and it springs back to exactly the same shape. That means the material is elastic. Okay, so steel is actually an elastic material. If you bend it and you don't bend it too much, you don't go past its elastic limits, it springs back. And that elasticity is measured. Sorry, we're going to talk about stiffness. Sorry. So the next one's stiffness. Okay, so what I'll do is I'll get you to pause the video there and just copy down each one of those, well, what's on the board now basically, but we're going to, after strength, hardness, elasticity, because we're up to the E, and she's the Prime Minister to defend the Northern Territory, we're going to do the S next. So I'll get you to pause right now and write that down. Okay, so we're up to this S here. So we've got two S's, one strength and the other one is stiffness, which is kind of the opposite of elasticity. If something is not elastic, material is not elastic, then it is stiff. Okay, so stiffness is the ability to resist elastic deformation under load, measured using Young's modulus. And that's sometimes referred to as the modulus of elasticity. So a little bit more explanation. When we're talking about elasticity, if I've got a steel beam, I'm going to change colours because this pen's running out. If I've got a steel beam and I apply a load and it bends, okay, and then I take the load away and it goes back to a straight line, we say the material's elastic. Now if I apply the same load but it only bends a very little, we would say that the material is stiff. Okay, it would have a high Young's modulus. So as you can see here, stiffness and elasticity are related. Okay, so we can talk about one and we can talk about the other at the same time. So that's our stiffness. The next letter in our acronym is P for plasticity. And that's basically the ease of moulding / / shaping the material. Now, plastic, it has the word plastic in it, so we know that with plastics, quite often if they're thermosoftening, if we heat them, we can pour them into a mold, they'll take the shape of the mold, and then they'll go hard and they'll no longer be plastic and they'll form the shape that we want. So clay is another material that's plastic as well. Before you fire clay, it's easily molded, and that's why we say it's a plastic material. So that's plasticity. Malleability. Quite often metals have this property, okay, malleability. It's the ability to be hammered into a thin sheet. Now, we know that metals like gold can be made into gold leaf because you can hammer it into a sheet, so it's quite a soft metal. Lead can be hammered into a sheet as well, so that's malleability. I'll get you to pause. We're nearly there. Okay, we're nearly through all of these materials. So I'll pause the video there. I'll get you to write down what malleability is, what plasticity is, and what stiffness is. And then we'll do the last 3 in our list. Okay, that last 3 are this D here, which is ductility. Now, most often ductility, D-U-C-T-I-L-I-T-Y, is ability to be drawn into a wire. So usually metals, if we've got a block of material and we start pulling on it, we can pull it so that it becomes a wire, okay? So it can be drawn out into a wire. Now, I used to always think, well, if it's malleable, it must be ductile as well. Quite often those two do go together, but for instance, the metal lead can be hammered into a sheet, no problem at all, but when you try and draw it into a wire, it tears. So they don't always go together. So the ability to be drawn into a wire is our ductility. Fatigue. Now, later on we're going to talk about loading materials and draw graphs of stress versus strain, all that sort of stuff. It's way further through the course. So all we need to know now is if you're within the elastic limits of a material, we're talking about elasticity, if you stay within those limits, the material always bounces back, okay? And you say, great, no problem at all. Keep loading it, unloading it, loading it, unloading it. And as long as you don't go past that limit, the material won't deform or break. That is true, but certain materials, if you cycle them even below their elastic limit enough times, they'll form cracks, and the cracks will get bigger and the material will fail. And this is something that we found out in the early days of jet aircraft, especially with pressurized cabins. You pressurize a cabin within its elastic limits, you unpressurize, pressurize, unpressurize. Eventually, because of that cycling below the elastic limit, the material will fail, and it's called fatigue failure. Okay, so it's a special type of fatigue failure. And if something has a low cycle fatigue, it means it will only take a small number of cycles before it fails. And I think the normal low cycle is about 10,000 cycles. Okay, so if something fails after 10,000 cycles of load below its elastic limit, we say it has a low fatigue cycle. So we're going to write, so it's basically applying load. You've seen, like, Kia, when they're testing a chair, they'll have a weight that constantly goes bang, bang, bang. Below the limits of the chair, eventually the chair will fail. even though you're way below the weight that it can hold. Okay, so something to think about in engineering. This is why bridges have a lifespan, even if you've got traffic below their limits. All this fatigue cycle situation is very relevant in engineering. Something that we really need to get our heads around. So it's the tendency. So fatigue is a tendency to fail when cycled repeatedly below the elastic limit. So that's our fatigue. So we've got one last one, which is the n small subscript t, and that is notch toughness. Now you can test a material to see how well it can receive a shock load, because some materials you can put weight on gently and keep loading it up and loading up and take a whole lot of weight. But if you drop the weight on and shock it, it will fail. Okay, especially materials that are brittle quite often will fail well below the load that they can actually hold if the loads are being applied statically rather than dynamically. Okay, so notch toughness is a measure of the energy required to cause failure. So they're all of your material properties, especially they're all the material properties on the left, and your mechanical properties using that acronym. She's the Prime Minister, defend the Northern Territory. That's a way of remembering some of those terms. Now, the reason why you might want to remember those terms, if you're asked to discuss properties of material, you start thinking, well, what words can I use? If you've got these two things down here, you'll never forget about things to talk about. You'll be able to talk about mechanical, magnetic, chemical, physical, electrical, and thermal properties of a particular material and decide whether it's relevant to the question. And you'll be able to also discuss all of these mechanical properties of a material. So I'm hoping that's a nice scaffold. If you make these notes carefully and remember those acronyms, you've got a big grab bag of terminology that you can use in your HSC. Okay, so do a bit of research on your own by all means into each of one of these terms, but that should set you in good stead for groupings of materials and properties of materials for your preliminary in your HSC course. And later in the course we'll be meeting a lot of these terms again and in more depth. See you in the next lesson. Make sure you get that all down. Pause the video when you need to, and we'll see you in the next lesson.